We discuss about Jacobian. Okay. When we solve various problems related to mathematics, so we need some transformation. So Jacobian is also the part of that. So here we take the help of determinant. Okay. So we define as for two variables. Basically, we start with two variables. If the variables u and v are the function of variable x and y. So we write down as u is the function of xy, and v is also function of xy. So here u and v work as a dependent variable, x and y work as a independent variable. So then the determinant of u v with respect to x and y is. So first take the dependent variable u, del u upon del x and del u upon del y. And the second row we take a second dependent value, del v upon del x and del v upon del y. So is called functional determinant. Functional determinant. Functional determinant or Jacobian. Functional determinant or Jacobian of the variable u and v with respect to x and y. With respect to x and y. This is denoted as del uv upon del xy is equal to, or we can write down as, or Jacobian of uv. Simply, we write down as del uv upon del xy or Jacobian of uv. So when we interchange row or columns in the determinant, so the value of the determinant remains same. So you can write down as, or Jacobian of uv is equal to del uv upon del xy is equal to del u upon del x into del vy or del u upon del y or del v upon del y. So here we write down as interchanging the rows and columns. The determinant value remains same. So this is the Jacobian of two variables. Two variables at u and v with respect to x, y. Now we move to the three variable case. So we write down for three variable if u, v and w be the function of x, y, and z. Then we write down a u equal to function of x, y, z. V also function of x, y, z, and w is also function of x, y, z. Then Jacobian of u, v, w with respect to x, y, z is, so we write down directly, so u, v, w, Jacobian of u, v, w can be written as del u, v, w upon del x, y, z is equal to determinant of, so here we make the 3 by 3 determinant. The number of dependent variable is equal to number of independent variable for making the determinant. So del u upon del x, del u upon del y, del u upon del z. Second row, del v upon del x, del v upon del y, del v upon del z. And third, del w upon del x, del w upon del y, and del w upon del z. So we can remember this first row. Okay, we take first dependent variable with respect to all independent variables. Second row, or second dependent variable with respect to all independent variable. Or third row, third dependent variable with respect to all independent variable. Okay, or similarly, you can write down in the form of interchanging the row or columns. So you can write down this as del u upon del x, del u upon del y, and del u upon del z. So del v upon del x, del v upon del y, del v upon del z, del w upon del x, del w upon del y, and del w upon del z. Okay. Now, we move to the general case, that means n independent variables. So let y1, y2, yn be the dependent variable. They are function of x1, x2, xn. So then the Jacobian of y1, y2, yn with respect to x1, x2, xn is, so Jacobian of y1, y2, yn can be written as del y1, y2, yn upon del x1, x2, xn is equal to determinant of del y1 upon del x1, del y1 upon del x2, del y1 upon del xn, del y2 upon del x1, del y2 upon del x2, del y2 upon del xn. Or write down the last term, so that is del yn upon del x1, del yn upon del x2 and del yn upon del xn. So this is the general term. So when we have n dependent variables and n independent variables, so we make determinant of n by n. Now we have some particular cases. We have some particular cases. So for particular cases, we write down as if y1 is a function of only single variable x1, y2 is a function of two variable x1 and x2, y3 is a function of three variable that is x1, x2 and x3, and similarly we write down for general term yn is function of n variable x1, x2, x3, xn. So then the Jacobian of y1, y2, y3, yn is equal to del y1, y2, y3, yn upon x1, x2, x3, xn is. So y1 is function of x1 only. So we write down del y1 upon del x1. Other terms will be 0, 0, 0, 0. Okay, y1 is function of x1 only. y2 is function of x1 and x2. So we write down del y2 upon del x1, del y2 upon del x2. So other terms will be 0. y3 is function of three variable. So x1, x2, x3. So we differentiate y3 with respect to x1, x2, and x3. So del y3 upon del x3. So other terms will be 0. And we write down the general term. So the general term, that means yn is the function of all n variable. So we write down del yn upon del x1, del yn upon del x2, del yn upon del x3, and del yn upon del xn. So we see that the upper triangular is 0. So we have the property of determinant when upper triangular of any determinant is 0. So the determinant value will be the multiplication of the leading diagonal elements. Multiplication of the leading diagonal element. So multiplication of the leading diagonal element. So these are the leading diagonal element. So that determinant value of this particular determinant is del y1 upon product of del y2 upon del x2 into del y3 upon del x3 into del yn upon del x. Okay, so you remember the standard result directly. So when we have such type of cases, that means particular cases, so y1 is function of x1 only, y2 is function of x1, x2 variable. So we follow the particular case. Okay, so on the basis of these cases, that means for two variable, three variable, n variable in particular case, we have some question related to that. So we discuss problems related to that. We start first problem of Jacobian. If x is equal to r cos theta, y is equal to r sin theta, so then find del xy upon del r theta. So here we calculate del xy upon del r theta. So we write down as the solution. So del xy upon del r theta. So x or y work as a dependent variable. So we clearly see that x is the function of r theta, y is the function of r theta. So you write down that x is the function of r and theta, y is the function of r and theta. So here we are going to calculate Jacobian of xy with respect to r theta. So first we make the determinant del x upon del r into del x upon del theta, or second row del y upon del r into del y upon del theta. So this equal to del x upon del r. So we differentiate x with respect to r. We follow all the rule of partial differentiation. That means when we are going to differentiate partially with respect to r, so we treat theta as a constant. So the differentiation of r is 1. So first term will be the cos theta and del x upon del theta. So when we differentiate with respect to theta, we treat r as a constant. So we write down r, and differentiation of cos theta is minus sin theta. Del y upon del r. So del y upon del r is sin theta, and del y upon del theta. So differentiation of sin theta is cos theta. Okay, see here we simplify the determinant. So we multiply of leading diagonal. So this can be written as r cos square theta minus off diagonal. So we have the negative sign. So this is also negative sign. So negative, negative plus. So this r sine square theta. So here we take r as common. So we write down as sine square theta plus cos square theta. So this equal to 1. So this gives us r. So the value of del xy upon del r theta is equal to r. So this is our first question, that we can say that a basic problem. Here we obtain the value of del xy upon del r theta. So we use the, now we move to the next problem related to that. So next problem is we have three dependent variable and three independent variable. So we take the problem related to that. If x is equal to r sine theta into cos phi, y is equal to r sine theta into sine phi, and z is equal to r cos theta. So we have the function x, y, z of r theta and phi. Now we obtain, so here we show that. So then show that del x, y, z upon r theta phi is equal to r square sine square theta. So we show that. So that means we take the LHS. So now we do the solution of this. So we take LHS. So when we take LHS of this is del x, y, z upon del r theta phi. So that means Jacobian. So we directly open the Jacobian determinant of this. So we write down del x upon del r, del x upon del theta, del x upon del phi. Second, del y upon del r, del y upon del theta, del y upon del phi. Third is del z upon del r, del z upon del theta, and del z upon del phi. Okay, so we solve this determinant. First is del x upon del r. So x is the function of r theta and phi. So when we are going to differentiate partially with respect to r, so theta and phi we treat as a constant. So del x upon del r, so that means theta and phi work as a constant. So differentiation of r is 1. So sine theta cos phi. The first term is sine theta cos phi. The first term is sine theta into cos phi. And del x upon del theta. So del x upon del theta. So sine theta differentiation is cos theta. So r cos theta cos phi. So second term r cos theta cos phi. And the third term del x upon del phi. The third term del x upon del phi. So this will be r sine theta. The differentiation of cos phi is minus sine phi. So this is minus r sine theta into sine phi. So this is our first row. Now del y upon del r. Del y upon del r sine theta sine phi. Sine theta into sine phi. Del y upon del theta r cos theta sine phi. So r cos theta into sine phi. And del y upon del phi. So r sine theta into cos phi. Third, del z upon del r. Del z upon del r is cos theta. Del z upon del theta, so minus r sine theta. And del z upon del phi is 0. Del z upon del phi is 0. So now we solve this determinant, 3 by 3 determinant. So this is equal to, for solving this determinant, so first term we take as a sine theta into cos phi, sine theta into cos phi. So for this one, so we do the cross multiplication of this into this. So first term is 0, 0 minus, so we have minus sign, so this is equal to plus. So we write down as r square sine square theta into cos phi, minus we have r cos theta into cos phi. And for this term, so we take as this to this, so 0, 0 minus this, so 0 minus r sine theta cos phi into cos theta. Third term is minus, or minus plus minus, so plus minus plus. We have minus, so r sine theta into sine phi, and the multiplication of these two terms. So we write down as minus r sine square theta into sine phi minus r directly cos square theta into sine phi. So we do simplify this. So this we can write down as r square sine q theta into cos square phi, sine q theta into cos square phi, minus, so this minus minus plus, we take r into r square, and the term, first term is just sine theta. Now second we write down as cos square theta into cos square phi, and for this minus minus plus r square sine q theta into sine square phi, and minus minus plus r square sine theta cos square theta into sine square phi. Now this equal to we see that this first term and third term. So we take first and third. So from first and third, we can take r square sine q theta as common. So when we take r square sine q theta as common, so this gives us cos square phi plus sine square phi. So this gives us cos square phi plus sine square phi. The value of this equal to 1 plus. Now we move to the second and fourth term. So second and fourth term. So from second and fourth term, so we take as r square sine theta, r sine theta into cos square theta is common. So this also we can write on cos square phi plus sine square phi. So this also equal to 1. So we write down the next step as r square sine q theta plus r square sine theta into cos square theta. So here we take common r square into sine theta. So the first term will be sine square theta and the second term cos square theta. So this also equal to 1. So this gives us r square into sine theta. So this gives us r square into sine theta. So our result is correct. So here is sine theta. Okay. So this is